Okay, welcome to the fifth main video in this portion on ST2 hypothesis testing. Please also see the demonstration videos for hands-on practice on doing things with RStudio to navigate this whole area. And that especially applies here with multiple test correction, that it's very, very difficult to do by hand for if you're doing many tests, whereas with RStudio, you can do things very efficiently. So our main basic idea behind multiple test correction is that if we repeatedly test a bunch of different samples during testing, as we say, we gain more samples, we keep testing the groups as we go along. So we might be doing a t-test where we're comparing two different groups and we're just gradually going from 10 versus 10 to 11 versus 11, 12 versus 12 during these different stages here. Because of the range of p-values we might get for a uniform distribution at the start, going from 0 all the way to 1. At some point, we might find that our p-value just happens to be small during this testing, but in reality, when we get to our final sample sizes, there's still no effect. We might spuriously choose this p-value threshold, this instance of the one we choose to report, ignoring the fact that we actually have done many samples, and we need to correct for this issue that we have tested many samples. And it's essential in any research paper, any research we publish, show, communicate, that we do this. So samples that are tested more than once, mostly we must correct for that effect of testing more than once. If the underlying data is independent, then we don't need to correct, but that means the data has to be completely independent of, has to be not tested more than once. And that will be rare in most biological contexts. And note that certainly if I'm editorially reviewing a paper or whatever, and there's no multiple test correction, that's a good grounds for just automatic rejection, because it's just not good practice at all. So we have this issue with false positives, and we can kind of think about if we do large numbers of hypothesis tests, we'll get many false positives. A traditional approach to this would be Brown-Ferroni correction. It simply takes the p-value and divides it by the number of tests we have. But in practice, that's too conservative. So we want to think about this balance of our PPV and our capacity to detect true positives and our power and everything. So this PPV is rated to a false positive rate and our precision. And what we want to think about is my p-value more extreme than it would be expected under a null hypothesis, given its rank in my p-value distribution. So we think that going back to this issue that we have our null distribution going from 0 to 1, and therefore if we have a flat distribution like this, we can rank the p-values as we go through. We can sort and rank all our different ones as we go along. And if we have another distribution mapped onto this, we're asking then, is my p-value more extreme than would be expected under the null hypothesis, given its rank in this distribution? So it's not comparing the actual p-value, it's comparing its rank relative to a reference point in a uniform distribution. So that means our reference point p-values here are all equidistant from each other and depends on our number of samples on the specific values that they have. So we're going to focus on is the Benjamin-Hochberg multiple test correction, which assumes our data is normal. There are other methods, but I would be cautious against ones that are too relaxed, because again, we just go back to this issue that would just get a ton of small p-values, and it can be meaningless at times. So let's say we have a bunch of 100 trees that where we're using this p-value threshold of 0.05 to understand our data better or select samples for further testing. The approach for the Benjamin-Hochberg correction method is to compare these against our reference set, and our formula for determining them is simply our rank by alpha over n. And that would mean this sense that we take our ranks and multiply by 0.05 divided by 100. So rank might start at rank 1 and then 2, 3, 4, 5, all the way down to 100. So that would mean our threshold p-value for the first p-value will be smaller, and then our threshold for the ones that are further down will be less small. So that will mean that our threshold p-value for the first one is simply going to be 0.05. this is 0, 0, 0, 5. And then our next one down is going to be, if my pen allows me to write, 0.00, oh wait, that's 1, 1, 0. And the next one down is just 0.5 further along the scale. So you can think of you moving along this uniform distribution, and then 0.0020, and then as you can guess 0.0025 and so on. So just progressively move along the distribution in this manner, and we compare our different p-values that we get. So we sort our p-values first of all and compare the smallest p-value against this value and see if it's more extreme. So that's our formula. They're ranked by alpha over n. So we sort our values, get their ranks, and compare. So if my smallest p-value is less than 0.0005, then I won't accept the null hypothesis. I'm not saying that we're going to test that further. And same for the second one, and so on. However, if we at some point k, we find that it's bigger than our threshold value, then we accept the null hypothesis for that one and then stop for the remainder. So let's say if we have a bunch of values where the first one is 0.001, that is less than our threshold p-value of 0.005, we say, yes, I'm going to not accept the null hypothesis for that particular sample. If our next one is 0.004, that's less than the threshold value of 0.01. However, if we meet the third one, it's 0.022 and our threshold is 0.0015, we'll say no, that conforms to the null hypothesis, and the remainder will be skipped. So in practice, what we can do then is obtain from RStudio our corrected p-values and our original p-values, and we can plot them. That's something we're going to do in the demonstration videos that you should watch. So what we're going to do is take our original ones, they're known as the raw p-values. We're going to plot them, and we're going to take the corrected ones. And what we'll see is that we tend to get values that, if we're going from 0 down here up to 1, and the same over here, is that our corrected values will always be larger. So you get a distribution that looks something like this. That's what you typically would get. So the original p-values may be very small, but typically after correction, you might find that they're much higher. And they'll be higher of a scale that approximates the sample size. So that concludes this video on multiple test correction. Please see the demonstration videos for hands-on calculation of all this in RStudio.